Hello everyone, I am Marouene, second year PhD student. I work under the supervision of Professor Pascal Lafon from the University of Technology of Troyes and Assistant Professor Julian Gardan from the Engineering School EPF. I am pleased to present you a section of our work on smart materials in additive manufacturing. My presentation today will be about the identification of elastic constant of a 3D printed pre-structured material using digital image correlation. My PhD work is part of the research project Smart Materials in Additive Manufacturing, managed by EPF and UTT. This project is interested in the development of digital models and experimental tests in order to optimize 3D printing strategies as well as to improve the mechanical and physical properties of printed parts. We are located in the northeast region of France, just 2 hours drive from Paris, in the beautiful city of Troyes. The plan of my presentation is as follows. I will introduce first the concept of the smart material and the main idea behind this research work. Then I will present the challenges with my PhD work and the adaptive methodologies. The identification of the mechanical behavior of a pre-structured material will be explained, followed by a numerical validation of the model, and I will finish with a conclusion and the future work. Let's start with the introduction and the context of the study. The requirements of the industrial environments are more and more complex. Advanced applications such as aeronautics and automotive, which required the implementation of complex assemblies of several components, present a major challenge for manufacturers. The integration of functional or smart materials is considered at this level as an optimal solution to meet these needs. Smart material can be defined as a static definition of complex shapes or materials combination to achieve one or more properties that respond to predefined functionality. Some examples are lattice structures, oxidic forms, and multi-material biotopological optimization. Here comes the importance of additive manufacturing, since it makes it possible to produce topologically more optimized and more complex shapes than with conventional manufacturing processes, and therefore allows the development of advanced materials. Our work deals with developing pre-structured materials using fused deposition modeling process. For this process, classical deposition with plus 45 minus 45 degrees angle orientation is commonly used thanks to its capacity to have higher infill percentage. Thread deposition can be not suitable to the mechanical constraint of a product, according to its use, especially when a weak coupling occurs between the filaments. Therefore, the filament deposition must be optimized through a new method based on the identification of mechanical stress fields from the product used. The key idea is to orient filaments toward tensile stress, allowing a strong coupling between the filaments similar to the principle of reinforcements of composite materials. An optimized method was developed based on reproducing principal stress direction inside the structure. Those orientations are obtained from the principal direction of preliminary finite element simulation under plane stresses for an homogeneous isotropic material. Since the filament has only one possible deposition angle, a layer alternation inside the structure is used between both principal orientations. In the region where principal stresses are the highest and mainly tensile, optimized trajectories will be generated. Previous work on a CT specimen proves improvement by over 20% of the fracture toughness, showing therefore the beneficial effect of such deposition method. For the sake of better understanding this beneficial effect, our strategy is to develop a numerical model based on mechanical characterization of the pre-structured material in order to have a predictive model that goes into fracture. Such model requires facing some challenges. First, we need to deal with the complex trajectories and the printing parameters, then characterize the mechanical behavior of the material. Once the model is fully developed, it will be used later on to investigate the optimized deposition method. Feasibility study was done consists on reproducing the printing trajectories inside a finite element model by assigning local references in mesh elements according to the intersection between the deposition trajectory and each element faces. As presented in the figure here, this method was successfully applied on a CT specimen and both principal directions are well reproduced. For further information about smart materials and optimized method, I kindly invite you to check the following references. In the next section, the methodology adopted for this work and the purpose of this study will be presented. Our model requires a specific work divided on three steps. One include the build anisotropy which can be judged as achieved. Second, we need to identify the mechanical behavior until fracture. Finally, we will use peridynamic simulation to model the fracture. Developing a predictive model of pre-structured material arises a challenge, especially identifying the inputs using different identification protocols and experimental methods. Various materials constants must be well identified, such as elastic constant energy release rate and bond properties. The purpose of this work is to identify the anisotropic elastic behavior of pre-structured material using digital image correlation. And transverse longitudinal and transverse modulus, in-plane Poisson ratio, in-plane shear modulus, and the Poisson ratio in the isotropy plane. For the methodology, first an experimental identification will be done through tensile tests with different filaments orientation. Then the identified elastic constant will be validated using an error evaluation by comparing experimental results with numerical results. A cost function will be defined based on difference evaluation between subsets data and integration point data. The experimental identification will now be presented. Here we start by printing tensile specimen according to the transverse and the longitudinal and 45 degrees direction. White ABS filament was used in purpose to have a better contrast while applying the black speckle. For every tensile test, three regions of interest will be selected. A method was used to access the true displacement of the specimen. Here, we note that we were confronted to numerous slip problems and filaments delamination inside the jaws of the machine. Then, a large region of interest is defined to get an average estimation of both longitudinal and transversal strain and therefore allows the calculation of the Poisson ratio. Using DIC, avoid the problems of placing a strain gauge on the surface of the 3D printed specimen since the surface is not perfectly flat and the delamination of filaments is possible. For experimental identification, three elastic constants are directly identified through tensile tests: longitudinal and transverse Young modulus and in-plane Poisson ratio. The shear modulus will be calculated through stress analysis of the 45 degrees specimen. For the Poisson ratio in the isotropy plane, we are working with a plane stress geometry and only performing DIC on the surface. As the following equations shows, this elastic constant is activated when we have off-plane shear loading or in-plane stress, or for the case of in-plane stress, we need to measure the out-of-plane displacement. For our study, we will use an average value between both values for longitudinal and transversal specimen. The shear modulus is calculated using the stress analysis of fiber-reinforced composite. Using a coordinate transformation of stress from global reference to the local one, we can calculate the shear modulus using both longitudinal and transversal Young modulus previously identified and the experimental value of the Young modulus of the 45-degree specimen. Now we go to the results. Reaching the plastic limit with proper stress and strain levels is crucial for our study. Since the ABS present a non-linear elastic behavior, two methods will be used to calculate Young modulus. The first one is a calculation as a slope of the tangent of the true stress-strain curve at a low stress. The second consider a linear elastic behavior that goes until the yield stress point. Values are then compared to literature showing some differences that can be related to printing configuration that can directly influence the mechanical properties. Although both specimen longitudinal and transverse show implicate different coupling between the filaments, the values of Young modulus are very similar. The elastic behavior of the pre-structured material can be assumed as isotropic, and the anisotropy was observed mainly with both yield stress and the tensile strength. For the last constant, we are working on an experimental setup to allow us to calculate it. The idea is to use a digital image correlation setup with two cameras that gives an estimation of the off-plane displacement. Next step is to check the validity of the identified elastic constant. For that, we will use the local reference assignment to reproduce the deposition trajectory into the model. The objective is to calculate the difference between the numerical and experimental force as well as the difference between the experimental strain field and the numerical strain field using the previously identified material constant. For that, a cost function was therefore defined and can be decomposed into a strain cost function that compares data between integration points and the subset from a snapshot, and the load cost function, which compare the experimental load and the numerical load. We also decided to evaluate the cost function on different loading steps. First, we perform a linking procedure between the subsets in the reference snapshot and the undeformed mesh. Here, the density of subsets is higher than the integration points, so we decided to reduce data size to fit the number of integration points by linking each one to the neighbor subsets. Also, 7 loading steps were chosen from the starting of the test to the yielding point, but later we discarded the first two because low strain values are easily perturbed by the noise of the DIC measurements, and the measured loads values are affected by the loading phase slip or the slip between the jaws observed in the beginning of the test. Here are the results for valid specimen. Sadly, for the transverse direction, only one specimen is valid. To compare both approaches, first, both approaches are giving accurate estimation of strain field. The nonlinearity observed with the true tensile curves is the main reason behind the high levels of errors for the load cost functions with both approaches. But the second approach is still giving lower error values. The nonlinearity observed with the true tensile curves is the main reason behind the high levels of error for the load cost function. At this point, by comparing the final cost function between the two approaches, and especially knowing the purpose of our study is to model the behavior until fracture, It's very clear that the approach number two is more appropriate to our project. So for that, this approach will be used. Now let's check the validity of those identified constants on a complex geometry. For different printing configuration, bending specimen for different printing configuration, bending specimen are chosen. Classical specimen at plus and minus 45 degrees, and optimized one are printed, and the numerical model are oriented. The following figures shows the oriented mesh elements of both numerical models. As we can see from the graph, both numerical models are giving similar prediction of the load, although the optimized specimens are stiffer than the classical ones. The model is for the moment not able to highlight the difference of stiffness that could be explained because of the almost isotropic elastic behavior. Now we finish by the conclusion. As we said before, developing our numerical model goes through three main steps and requires the identification of various inputs. For the built anisotropy, we can say that our method is efficient and allow us to reproduce complex trajectory in the finite element model. Another important finding is that the elastic behavior is almost isotropic. What we have developed for the cost function evaluation can be obviously used to re-identify all four elastic constants at once via a finite element method updated identification with an optimization method on beam or CT geometry with a specific choice of region of interest according to local loading states. A work in progress consists concerns identifying an isotropic yield criterion, which is the Hill criterion, and the plastic model that goes into crack initiation. Then, the next step will be to model fracture using peridynamics simulation. The peridynamic simulation theory is an extension of the standard theory of solid mechanics compatible with discontinuities due to the presence of cracks. The principle is to treat the material as an assembly of discrete points linked together by specific bonds. During deformation, when the deformation exceeds a certain bonds will break and cause nucleation or extension of the cracks. Consequently, the initiation and the growth of cracks spontaneously emerge from a peridynamic simulation without the need to define beforehand an initiation and propagation criterion, which requires a lot of experimental parameters. The idea is based on a preliminary work. It's in our internal work, which consists in using a peridynamic box coupled with a calculation by finite elements in order to follow the propagation of crack. If you have any question, you can send me an email on the following email address. Thank you for your attention.